Good afternoon, everyone. Thank you for coming. It's great to see so many people here, with familiar faces and some unfamiliar faces, and also kind of all the lecturers. Thank you very much. We, as you would have seen from our email that we sent out, we're very lucky to have Professor Schmock here from Vienna and Austria. He's got a PhD and he's financial risk management in actuarial science, and he's also the Vice President of the Actuarial Society Actuarial Association of Austria. He's going to have two presentations today. The first one is slightly more technical on Poisson mixture modules. So that will be the first presentation, about 30-40 minutes or so, and there will be some time for questions afterwards. Then we'll have a quick break, and then the second presentation is more kind of related to actuarial science, and then the setup in the EU and Austria. So talking about what's interesting. So there will be a quick break, a short break between these two presentations. Well, thank you very much. We're looking forward to it. Thank you.
So thank you very much for coming. And I'm sorry for my German accent in English, but I didn't work with English, so I had to learn it through it. So anyway, so thanks to my colleagues for giving me the opportunity to give a presentation here. I'm trying to choose a topic which is not too boring for my colleagues, but also kind of understandable to students. When you try such a compromise, you might not please everyone. I know, maybe you please no one. I give it. So I picked the topic which I worked on together with a master student of mine, Karoline Vonach. She's finished 1.5 years ago. She also gave a talk at an international conference on that subject. And I have to say she is a very talented student. I wanted to keep her for a PhD, but I don't know. She was attracted so much first to travel in South America and then go to industry. So she doesn't want to do yet a PhD. That's our research group for financial actuarial mathematics. It's within the Vienna University of Technology. So nowadays, university have a brand name. The brand name is the German abbreviation Technische Universität Wien. Here, that's the homepage of our group, and you are very welcome to visit that one. Okay, let's go into it. It's about matrix value gamma distributions in multivariate Poisson mixture distributions. As a short introduction or a brief recall, maybe we start here. So just recall the definition of a Poisson distribution. So the probability of a random variable, which is Poisson distribution, is parameter lambda. So you can calculate that probability, and it's given explicitly by the right-hand term. And you use it for modeling claim counts, the actuarial science. In mathematical finance, you use it to model the number of credit defaults. Mathematics is the same, but you just call it differently. And the Poisson distribution has very nice properties. So with respect to the parameter, it's a semi-group, but we have two independent Poisson distributed random variables. If you add them, it's again a Poisson distribution, and the parameter is just sum of the two parameters. So it's a semi-group, it's also infinitely divisible distribution, and most importantly, there's a Poisson limit which justifies using them. I'll happily give a talk on that, but it's not complicated. Then you know the exponential function, the logarithmic function, the trigonometric functions. You should also know the gamma function. So the gamma function, depending on the parameter alpha, here the talk today will be a strictly positive real parameter, is given by that integral. Of course, this means how to do the integral and calculate it. Of course, you can do it for alpha equal to 1. You just have to integrate the exponential. In general, you can't. And you have to accept that integral there is different. If you want to have a picture of it, maybe that works here. No, not quite. So the positive alpha, see that it's going back. Okay, so what you can do is here on the positive half line, the function here is never negative. So you can use it as a probability density. Of course, it doesn't integrate to 1 because it gives you the gamma function, but you can just normalize by the gamma function. So think of C equal to 1. So goes away, then you see the density from up, the function from up there, and normalize it's a probability density. So you can use it as a density for probability distribution. It's called the gamma distribution. And you can add a scale parameter to it. So then that changes slightly the definition, but with an integral substitution, you see it's still probability density. Also, the gamma distributions have very nice properties. With respect to the J parameter, they form also a semi-group. And these distributions are also infinitely divisible. And why do I introduce it? Well, when you want to model plane counts with a Poisson distribution, we calculate expectation and moments. In both cases, expectation and variance. In both cases, you get the lambda, you can fit by the method of moments. But then you notice that you have real data that what you estimate as expectation and as variance is different. Variance is often larger than the expectation. So Poisson distribution doesn't quite seem to fit. And what you can do is you can say, well, maybe that parameter is not really a constant. Maybe it's a random variable. And yeah, a non-negative random variable. Here you can take such a gamma distributed one and say, well, if I would know that random parameter, then I assume it's possible. But in reality, the parameter up there is a random variable. So when you then want to calculate the distribution, you can do that by first inserting the condition, that's the general rule. And then, well, condition is also distributed, so you copy the term from up there, now with a capital number. And then you have to calculate that expectation. And yeah, don't do that in your mind. It's a longer calculation, and you find the term on the right-hand side. If you look more closely, you see it's a negative binomial distribution. Where the P is an activation here coming from the scale parameter of the gamma distribution. So if you are studying actuarial science, all that should be familiar. So I can now say I'm just generalizing that slide to general dimensions. Finally, many dimensions. That's it. And if you know how it works, you can now read your email or whatever. Okay. So let's after that brief recap, let's go to the contents. So I will give you a short introduction. Then there's a technical issue I have to mention. And then instead of the gamma function you just saw, I will look at the multidimensional one. Then I use the same trick. I just normalize to get a multidimensional distribution. So that's how I get matrix valued gamma distributions. So definitions and basic properties, and probably I skip that property. And then hopefully we come to applying it to have again Poisson mixture. So let's see time permitting how far we get. So basically that background I gave you already. Models are popular, mathematics and calculus model. It allows you to capture some heterogeneity in claimed frequencies. Gamma distribution is often used without the negative binomial distribution, and as I just showed to you. And now we want to have that multivariate, because when you have claims, maybe they come from different insurance products. So you would like to model them together. And assuming independence is always a quite strong assumption. Same with credit losses. We have a number of credit losses in one rating class, and you have it in another rating class. They are dependent. Would like to model the dependence. I'm stressing that part. Have to look at dependence. Otherwise, it can be completely off. So we want to have dependence, and that's why we want to go to multiple dimensions. Here you can get quite a selection of covariants, such as so far we will only look at positive dependence. Otherwise, we have to use a technique which point in my lecture notes and share this model. So and here we want derive the dependence from these intensities by using a matrix where you gamma replacing the one-dimensional distribution by a matrix and that. Okay, so that's a quick look at the summits we are aiming at. So we can have more sophisticated dependence structures. We can have negative binomial distributions with different scale parameters. There are some disadvantages as well. And here, maybe it's nice to look at these two pictures. What you can always do if you want to have two dependent negative binomially distributed random variables, you can start with 3 of them, all independent, and here have one variable influencing both components. So that gives you the dependence of the two components, because the third one is in both. And here's the result what you get. So the diagonal, you have lots of probability mass. So off diagonal, the first one also quite high, and the remaining part is quite flat. And if you do the same, so same correlation, same marginal distributions with the approach of a matrix, gamma Poisson mixture, you see it's really a smooth hump. And note the different scales here. So it's really smooth hump and not so handmade as here with a brute force. It's more elegant of it. So that's what you're aiming, that's what you want to understand during the topic. Okay, so we need metrics value channel value. Okay, you know about matrices. So we need a special subset of them, namely, here we always have reason. We would like to look at the positive definite one. This P times P size. And so what's a positive definite matrix? It's always supposed to be symmetric. So if you transpose, say it's the same. And if you multiply with a vector from the right as well as from the left, the same vector, you always get something non-negative. And when it's positive definite, you get something positive, simply positive, unless you take the zero. So that's the subset of all these P times P values. And since these are symmetric, and somehow ignore the upper part of the diagonal, because you know it's a copy of the lower part. So you can use them also as a subset in smaller dimension. And when I do that, I have a tilde after it. And then there's a mapping between these two. So in one direction, from here to here, it's just copying the numbers to make from the triangular shape a rectangular one. And then the other way, just skip these numbers, because it's redundant movement. Okay, so and what will show up is that we have a function defined on these positive definite matrices. It's allowed to go to the complex numbers. I looked in your curriculum, complex numbers. And then you write down such a kind of integral, and it's mystery of integrate over a set of. So one way is to start from the map into the set up there and then integrate. To do that, there's a factor showing up, but you can here use really the back measure on that space. But the set here is looking kind of complicated. And even better method is to use the so-called Koleski decomposition, which means you can factor such a matrix into a product of a lower diagonal matrix and its transpose. And that is positive definite, that representation is unique. And that you can easily use actually calculate such integrals. The formula, probably you have to integrate over a submanifold of the big space. It's a little bit complicated. You actually have to know how to do that. We teach that as one of the parts in calculus 3. And she had forgotten about it, so I reminded her. She said it again, and then they were doing it again. But yeah, turns out if worried about climate warming, well, maybe you want to calculate the average of the temperature on Earth. So you have a function for every point on the surface of the Earth, have temperature. Then you have to integrate over the surface of the Earth. was particularly very good. And what kind of integration and also okay, so that's one you have to get used to. And then here I showed you the definition of the gamma function. So on higher dimensions, again, instead of the open half-line from 0 to infinity, you now integrate over these positive definite matrices. That replaces the strictly positive numbers. Then you integrate each the minus x field. So one dimension you don't see a difference. In higher dimensions, you can, when you have a matrix, you can take the trace and we also add the numbers on the diagonal of the matrix. That's the trace. If it's a 1 times 1 matrix, you have to do nothing. And here we also have the x with power alpha minus 1. Here, for p equal to 1, we see it's minus 1. That's the definition of the gamma function. Several dimensions is not complicated. And here, yeah, you have to do something with the matrix in order to. Yes. Oh, what you can do is you can calculate the determinant. That's slightly more complicated. You also learn that in the algebra, I checked your political determinant Schmock. So instead of the x here and here, you now have two quantities that you derive from the matrix, the determinant and the trace. And then you have to do that integration. There's a mathematical machinery doing. And yeah, if you like, don't like it, there's a formula for that function in terms of the gamma function I just gave you. Just a product of gamma functions and some constant. And we're happy with that one. And to do all the important things later on, we will need to calculate that integral. It's very similar to the one up there, but it has a matrix Z. The matrix Z can have complex entries. The X needs to be from that set, positive definite matrix. And the imaginary part needs to be a symmetric. That word symmetric was missing in the book we first used it. Caused lots of problems. So until we discovered they just had skipped the word symmetric. Okay, you need that one to be symmetric. Then you know you can calculate the determinant. It's not equal to 0. So you can divide here. And you can calculate that integral. And instead of getting the multidimensional gamma function, you just get one factorial. So that's magic. Just have the matrix there. Seems impossible to calculate it, but you can. And it's just such an easy thing. So there must, if you find such a thing, there must be more to it. Must be more to it. Okay, so here again, since it's positive definite, the determinant is always strictly positive. This is also strictly positive. So you can use that and normalize to get a density on that set. So that means you can define a new distribution on the set of these positive definite matrices. And that's subspace somehow of all the p times p matrices. So that's very similar to the density of the one-dimensional distribution. Just that the x is now replaced by the trace and by the determinant. And that works with the parameter here. Is not the alpha is not too small, and we consider that as a matrix value gamma distribution with shape parameter alpha. and here the identity matrix in dimension. Okay, so that's the standard matrix value gamma distribution. So one dimension you can have the scale and just multiply by the scale to get the general gamma distribution. So what do you use as a scale on matrix value? Well, what you can do is you can take a matrix C, which you can hopefully factor in such a way as a matrix times its transpose matrix. The A doesn't need to be a square matrix. And use it to transform the matrix value distribution from here, from the left and from the right, with that matrix A. And every random matrix value random variable, which you can represent in distribution in that way, you call matrix gamma distributed. And you write without a C, the Y matrix gamma distributed with scale alpha, with shape alpha, and scale matrix C with you can factor on this way. Of course, you have to prove that since there are different factorizations, that they all lead to the same distribution. Just to be clear. Okay, so that's basically from the reference, but there it's for the C to be positive definite scale matrix. And we include here the degenerate distributions as well. And that was her main task, to have the entire theory extended to these degenerate cases. Okay, here's a picture. As far as you can picture a distribution, even in 2 times 2 dimensions, it's a matrix with 4 entries. So it's an object in 4-dimensional space. Okay. But remember, it's a symmetric matrix. So we can skip one entry, then we are in 3 dimensions. 3 dimensions, we can make a picture. Okay, here it is. There is, so we have here, sorry, projection doesn't give us all of it. So the upper one here is just a copy of the lower one. So we can here see the 2 diagonal entries. Here the off-diagonal entry. So for that matrix to be positive definite, you have to stay to the right of that gray area. Only there, these 3 numbers give something positive definite. And then you can draw level lines. So how high is the density? You see here, it's the highest point. It's the maximum of the density. It's located there. And the other level sets here comes at 0. Same picture, but with a cut. Here is the highest value, then it's the level lines. And here, that's the boundary there. So maybe that's the best intuition, I think. The first non-trivial dimension is already a little bit hard to visualize. They gave up higher dimensions. Okay. So you have probably seen characteristic functions of distributions already. And you make learn that they need to characterize the distribution. So one task is now, of course, for the matrix value gamma distribution to calculate the characteristic function. Of you did it. And normally it has a real number here or a vector. Now you have to put a matrix on them. The symmetric one is good. So that means you have to calculate the expectation of the exponential of I, the imaginary number, doesn't matter whether it's there or there. And then you take the matrix product of C and the variable and take the trace and take that expectation. So it seems to be tremendously difficult to do that. And with the formula I showed you already, that's what you get. And I mean, somewhat can be easy. I mean, that's the identity matrix in P dimensions. In Z you put in, the C is a parameter matrix, the imaginary unit shows up, and of course, here the shape parameter shows up, but otherwise, very easy, given the complexity of the form. And that's also why you see that the exploitation of the C, the definition, doesn't matter. Because here in that formula only the C shows up. The C uniquely determines the A is not important. Yeah, and given that definition, you can even go one step further. There are some degenerate distributions which give you the same characteristic function at half integer values. So what I have done here starts with the rank of the scale matrix, -1 positive part half. From there on, the definition I gave you applies. You can have additional values of the shape parameter in the set.
Why does that has to be a real value in that translucent function?
What do you want to do?
Why does it have strictly does it need to be a real value? Yes. Yeah.
Yeah, this one. Well, it's symmetric. The theorem I showed you before lines. Here. The imaginary part was supposed to be symmetric.
Yes.
And if that's not symmetric, we don't know whether the Z can be zero determined. For example, so that's why we calculated only for the symmetric. And yeah, these distributions are coming from Wishart. The Wishart distributions derive from normal distributions. You can find all the details in that thesis. It's amazing. That's okay. Maybe I have time. Some properties. So there's a scaling property of these matrix gamma distributions, including these general cases. So if you take any matrix and multiply from the left and the transpose from the right, they don't need to be quadratic. You get again the matrix gamma distribution. So it's a nice family. You have a summation property as you have for the ordinary one-dimensional gamma distributions. So if you sum independent ones with the same scale matrix, just add shape parameter. When you switch components of the matrix with the permutation matrix, yeah, you again get the matrix gamma. Just here the scale has to be switched accordingly. So that's what you'd expect. You can, of course, calculate expectations and covariances of the components of that random matrix. That's what you get. And the C's are the components here of the scalar. So very explicit. And if the scale matrix here is positive definite, and you are not convinced of this, that's large enough, you have a density. And when you look into books, they often use that density to define it. So they don't cover the degenerate cases. We cover them all, and in a special case, we have a density. Yeah, and what's really surprising is, if you look at the probability generating function, sorry, other direction. We look at the probability generating at the continuity function, sorry, it looks it's the same for all the positive alpha. So why shouldn't there be a distribution for every alpha as we are used to it in one dimension? Why? And there's a paper published really in the first range probability journal showing indeed these very gamma distributions are not instantly divisible. So that was really new to me. If you would have asked me before we worked on that to come up with this, I would have said, no, I don't believe that can happen. And here's an but the theory is deep, so it's really a top end balance of probability. It's an easy goal. Okay. I think at some point I hurry up a little bit. So there's also a matrix valued exponential distribution. So with the special value here of the shape parameter. And we figured it out ourselves. Maybe it's somewhere in the literature. Otherwise, we should publish it. That valued exponential distribution is also memoryless. You know that from the exponential distribution. Memoryless distribution. And in the arrival times of a Poisson process of an exponential distribution, this waiting time paradox, you come to a bus station, you always have to wait quite long. Because there is no memory of how long, how much time passed already before you came, when they come, like the points of a Poisson. Because the exponential distribution is memoryless. And also the matrix value bound is memoryless. Of course, you have to use an order for matrices, and that's not much. But just for this. Okay, there's also some kind of fun we had. So when we now have a random matrix, we can look at the trace, we can look at the determinant. These two terms show up in density. So what's the joint distribution of the trace and the density of that random matrix? And yeah, we are able to calculate it. And if you have nothing to do for the rest of the week, or maybe in the next hour, depends on wherever you are, you can generalize that problem from 2 dimensions. We have solved it to higher dimensions. Here is a plot of the density on the region where the density is from. Even coming up with a plot was a problem, but now we have it. Okay, bias distributions, I think I skip. Go to this function distribution. So here's basically what I showed to you on the slide. So you condition on gamma distributed one assume it's Poisson, and what you then get is a negative binomial distribution. Here the C is called beta, okay. Success parameter is the P. Okay, and that's what we want to generalize. Now, yeah, we do that. First step, the other step I will not do. So we start with the dimension P as a number of random variables we want to have at the end. So then we start with a random matrix, which has a matrix gamma distribution with shape alpha and scale matrix C, which is positive semi-definite, allow for the general case. And then now we, for every I, set from 1 up n, we take a vector of the corresponding dimension which fits to the matrix, and we define a random variable lambda to be that random matrix multiplied from the right by the vector, gives again a vector, and then we multiply by the left, same vector or take the inner product, standard product as you like. That gives us real valued random variable. And since the y is always positive semi-definite, it's always non-negative. Because remember the definition said it's positive semi-definite if multiply same vector from both sides to get something non-negative. We build into the definition, we know this one is non-negative. So we can use that random variable as random parameter for Poisson distribution. So now we assume this n1 up to n conditioned on the random matrix have a Poisson distribution with that random intensity, and we assume them to be conditionally independent. Overall, there you have to put in some independence. And so the joint distribution of these n1 up to I, we say they are matrix gamma Poisson mixture distribution. And now that depends on the shape of that gamma one, scale matrix, and the vectors you choose. So from the scale property I gave you for matrix gamma distributions, you immediately get that these lambda I, you have them gamma distributed. And that's the corresponding scale parameter. So that means you immediately get that these components here with a negative binomial distribution is a formula with a parameter divided by 1 plus the parameter. The alpha of gamma distribution. So you now have a collection of negative binomially distributed values, which, however, are dependent because they come from the same matrix. Now we have a nice one. Dependent negative distributed ones. Fit that to the data you have to cover dependence. in a model. And that's always the tricky and important point. That's the dependence. So some say the financial crisis in 2008 came because people had a wrong model for dependence. Just said they're using a computer, it was a Gaussian. So dependence is very important. And here you have tools to capture. And that's what you do first. You first need a model. You have to think of dependence, you need a model which is able to capture the dependence, and then you try to fit it. So very intelligent guesses about the dependence. Here's a tool. You have that dependence. Okay, so I think at some point I should stop. Yeah, here is when you do the independent case. And here again, I showed you that picture at the beginning where you have dependence. It's nice and smooth. I mean, it just, you see here, the independent case. And here it's slightly shifted to have dependence. It's nice. That's not so nice. Yeah, and now you can go on. Completely generating functions of different variables. Kind of more complicated, so complicated. What you can read off is when you know what it, that the model is not quite identifiable. Statistical language. That means when you have parameters, you can take an orthogonal matrix and the model transform parameters, and that way is the same distribution. So maximum likelihood fitting might be a problem because it's constant mass. Okay, I think I stopped at this point. I explained the model. You can go ahead. You can have a multivariate Poisson distribution and put it in there. So that's after the references, the slide after the references. Here, some of the references. So here's after thesis is online in our library. I'm just 2 clicks away from my initial homepage. There is supervised thesis. Click there, then you get the list. Search for a name of that's the solutions. So click once again our library system. Okay, so okay, so I stop here. Thank you for your attention.
Thanks a lot. I don't have any question, but maybe from my side, I see the thesis, it says the applications and risk management. Maybe in 1 minute, maybe so tell us has been applied.
Yeah. I somehow advance my students to have a catchy title, and when it looks too sophisticated, then when you apply that practice, they might say, well, what does that have to do with us? So, of course, risk management is important in the financial sector, so it's good to have that. And also the Actuarial Association is giving out prizes every year for the 3 best master and PhD students. And also to attract their attention as jury, I'm not in the jury, attract their attention, it's good to have it kind of, application is good. It's good for application. Okay, let's look at it. And because otherwise I think, just mathematics, these are methods very good. Why should we care? And it says applications of risk management, and then writes report about it. Also stress it's important for applications. Then hopefully they also find it useful and give a question.
Did you consider a more general Wishart process rather than considering only metric gamma.
I mean, these metrics gamma are generalizations of visual distributions. We didn't consider it on the process surface. As a topology, it's one field. But good question. Maybe we should do that. And also that generally less. There is so much about theory which comes out that of the fact that the exponential distribution is numerous. So there should be lots of applications. I didn't have the time to work out the AXN.
Thank you very much.
You had few matrices that had complex numbered entries.
Yes.
What do those complex numbers represent?
And nothing to do with data. It's just here. The characteristic function of the I here you can take out. And when you have done it, then you see the absolute value of what we have here is bounded by 1. And that means since measurability is not a problem, you can always calculate the expectation, it's well defined. So it's a well-defined function for all these symmetric matrices. And to do that, I need the imaginary infinite there. So it turns out there. And for that reason, I need in this formula here, I need to be able to do it for a matrix which has the imaginary, non-vanishing imaginary entries. So it's purely technical, nothing to do with data initially, but it helps us to identify and work with the distribution. It's a mathematical tool. And I have no idea what to do without it. Of course, you can always try to get away with real and generic components, but I guess it is. So it's good to get used to complex numbers. Yes, now quantum mechanics becomes more important. Quantum science maybe. If we look at quantum mechanics in physics and physics, so it works with complex numbers. That's a complex valued function. It's this everything square of it gives the probability density for the particle. Then you look at Schrodinger's equation. So our cafeteria is called Schrodinger's cafe. They have, of course, Schrodinger's equation on what do you call this on the bar? Schrodinger's equation, and it has the imaginary unit in it. So it works with complex numbers. Also electrical engineer, and they describe electric current, which is the English current alternating current. The best described is by complex numbers. Patients get much easier. So in physics, it's true that in quantum mechanics you can't do without. So often in mathematics, many nice results you need complex.
Thanks, so it's just after 3, so we can quick break or back again after the second presentation. Thank you for the answer.
Do we have the second talk also online? Or?
I actually don't know. It's Matthias. I'll ask him. Matthias organized the.
I went to Tuesday, I in einer halben Stunde ein Video call.
Okay.
Hab mich gefreut.
Okay, good.
Ja. Okay, das würde man nicht predigen.
I'll just quickly see if Matthias can. Yeah, I think maybe we'll speak better on if that's okay. Okay, thank you very much. So, hello. Thank you. Everybody, thanks. Right, let's start, please. Cool. So, lots of thirties that have not joined us, and to kind of introduce you again to Wishart from Vienna University of Vienna. So the second session is a little more, is about the actual profession in Europe, and in particular, it's focused on second. So, thank you very much.
So, welcome to the second talk. It will be quite different from the first one. One technical, I think no formula, no proof, no theorem. I apologize for that. And I was asked to give you a short introduction about actuarial education in Europe and in Austria in particular. And yes. I have to distribute some of these. Please remind me. Okay. Yeah, I had some experience with profession and vice presidents and quite some time already, because as a university professor, I have the possibility to be vice president of the society. I was heading the education committee of our association for quite a while, Now I hand it over to a younger colleague, then she will replace me in the not too far future. And yeah, I will briefly talk about actuarial associations and the core syllabus. I apologize to all colleagues who put lots of work into these societies and which I don't mention here at all, work they've done and so on. I want to concentrate on the education part. Even there was so much work done, I can't describe it here. So I apologize to all these colleagues who have done work here. I just want to give a brief impression. Then I come to the actuarial education in Austria and what we require, what we offer, and so on. And the third point might be interesting to colleagues, namely how to attract students to study mathematics. Because in Austria, you have to study mathematics and become an actuary. And once studying mathematics, you have different directions to attract them to financial actuarial. That's my last part. My talk is so interesting for students, but maybe later you can run to a similar talk. Okay, so the International Actuarial Association, quite an old one, is an association of actuarial associations. Like United Nations, consists of nations. So far, if I trust Wikipedia, it has 73 full member associations and 24 associate member associations. That's quite fulfill the requirements or don't want to be full members. So quite some number of associations. And as an individual, can be a member through your association, and you can join one of these sections they have. So if you are, that's the oldest section, the Astin section, actuarial studies in non-life insurance. There's an Astin bulletin, you might know, already published. There are other sections you can join depending on your professional interest. Or if you want to have a say on international regulation, for example, international standards, that's a way to go forward and try to make it all right. But that's let's look at the core syllabus. It comes in two parts. Education guidelines and the education syllabus. I have links underneath the principle. I can click on them. Of course, there's a kind of consensus between very different associations and opinions. So you're sitting, normally a colleague did that once I replaced him, so I was sitting at such a conference. So there will be people from South Africa, Australia, Korea, Japan, France, Iceland, Germany, of course, Austria, France, and you talk about education. And the role of actuaries is differs from country to country. Of course, there's a core competence area. But whether certain reports can be signed by an actuary, have to be signed by an actuary, what kind of how the examination is taken. If you take it at the university, like Austria, if the society is running an educational academy, or in Africa, running such an academy, or whether it's a state examination that you have to pass. It's different in different countries. You can't just change how that specific country works. You have to accept it, you have to somehow root it. So that has to be done here, and for those of you who might want to be active or to be active in the future, as a senior person, if you are heading your educational committee, you hardly have an influence. If you want to have an influence, first, you have to devote lots of time. Next, you have to form coalitions with other associations. So you have a group of associations with a very similar opinion. Then you can push this, not with your individual opinion. So our representative formed, tried to form a coalition or formal talks to other people. Then he got our education committee to have printed statements that the head, the governing body of our association said, yes, that's our wish. So comes the power of the entire association into the meeting. When you form a coalition with other associations, you can move. Otherwise, you will get disappointed. So, if you want to have influence here, you really have to. Okay. Yeah. Of course, actuaries need competences in several areas. We were pressing for a strong mathematical background and the understanding of the models. Because an insurance company, if the actuary doesn't understand it, no one else will. So the actuary is the last line of defense. The actuary doesn't understand the mathematics and the model he or she is using, everything is gone. Up there might be some more ventures, but they don't care about the details, like model independence. The actuary doesn't do it. No one does. So here it's very important. So I consider the actuary as the last line of defense in the insurance. The actuary has to stand up and say, well, these are the risks. And when we have money, everyone wants to get money. Even the state wants to get money, because when the insurance company makes a surplus, the state wants to have taxes. The actuary has to say, stop, here's the dividing line, here are my actuarial reserves. These I need to pay future obligations. Okay, it's a small part, we can pay a bonus to managers, we can pay taxes on it, we can pay dividends. Here's a big chunk are actuarial reserves. And he or she has to stand up and say, here's the dividing line, don't touch. Everyone wants to touch. You have to stand up as the actuary and say, well, don't touch. Otherwise, they don't stop. So that's an important role of the actuary. You have to defend the actuarial reserve, in particular in life and health insurance. Big amounts of money have to defend that money. Of course, there are other areas you need to understand the legal framework you are working in. Insurance company is in competition with other companies, accounting rules and so on. You have to understand some software and IT systems. But here you have lawyers, here you have economists, accountants, here you have computer experts. So here you have to just work with them, talk to them. Here, that's and I think nowadays AI tools become more and more important. So when you get a maybe it's a fake picture of a car accident which never happened. Peaks have seen it. So we need to be aware of fake things. So far it's not in our group, but really, then we have to go forward here. Okay, so in principle, we can look at the course syllabus if you like. That's how it looks like. Statistics and so on. And of course, at the end, it has an appendix, foundations in mathematics. So our association was favor of these foundations. And yeah, integration, complex numbers, it's all there. Real and complex numbers, matrices. Okay. So all the topics in there, in the syllabus, I don't want to go through all the topics, way too many. I admire the colleagues who already wrote up all these topics. And somehow, oh, please everyone. This is the things in there. And then when you have a topic, you have to specify, well, should it be mentioned in 2 minutes? Or should it really be something serious you study for several weeks? So you have to say how deep you go into certain topics. And so they came up to use that revised Bloom taxonomy. So there's a 24 entry matrix, with 2 dimensions, names for it, knowledge dimension and cognitive process dimension. And so we tried to have something that said speed 3. And that really helps us. Oh, but I mean here, you know, some text. Here you understand the concept between the facts, how you go about it. And here, metacognitive knowledge also says you are aware of what you don't know. That's very important. Sometimes I see young students who think, well, they know everything. No, they don't. Even in my area of expertise, I know a lot of topics I don't know. Or I know the headlines. I don't know the topics themselves. So it's easy to meet a colleague, even in probability theory, and we can't really talk to each other. And if they are not a probability or statistics, I mean, so even in mathematics, there are dozen pages of just headlines. How mathematics is classified. And my PhD thesis is the one of these tiny headlines. And there is probability theory. Okay, I know some topics there, Professor nowadays, some experience, but there are so many topics I have no. You ask me about what's the basic definition of that area. And similar as an actuary, you should understand that there are many areas you didn't learn because there was just not enough training. And if the problem comes across, talk to a colleague, maybe talk to a former professor at university, consult the literature. Okay, nowadays we ask ChatGPT, I know, but sometimes you get out nonsense. Don't believe it. We should be able to check them, and I can help you. Okay, so and here are different stages. Here that's just or something. Remember, here you can at least discuss an example, or you can even explain it. Good. Yeah, some people are good at saying they explain, but when it comes to applications, they have a problem. So if you see something applied, yeah, to more levels, so our secretary says, no, why do you think no don't come up with a grade for that diploma? So I tell you, well, I have to read it. Well, it can't be so hard to read. You know? I'm here and trying to understand, well, what could be done more? What is possibly wrong, what is very precise, and so on. And yeah, here, create. I mean, creating a diploma thesis like the one I talked about an hour ago, that's something shouldn't be. Or coming up with lecture or a topic, which is not just a. So there are different levels. And every point is that our syllabus comes with a corresponding either corresponding letter and number, and yeah, you have to compromise there. Okay. The next Actuarial Association of Europe, it's Lange changed the name twice, now called Actuarial Association of Europe. It has Wikipedia statistics. Members of the pro-member associations, so many associations from European Union countries, but also Switzerland, Norway, okay, it's not in there anymore on free will, Iceland, Turkey, and so on. So it's really European, not just European. There are also observer associations like Malta, that's a European member state, an island state. Already it's too small to be full member. Ukraine and so on. So the initial purpose of the Actuarial Association of Europe was to give independent actuarial advice to institutions of the European Union. It's a kind of commission ruling certain things as the European Parliament and give advice. So nowadays, of course, so there are also sections similar to the International Actuarial Association. So we can work in sections, go to their meetings. There's an educational committee also in the actuarial associations. So the European Association maintains a core syllabus, which is, of course, contains everything which is in the international core syllabus. But something more, often topics are supposed to be studied more detailed, deeper, so it has a higher letter, higher number. And the aim here is to have the mutual recognition. That's, I think, the biggest plus for our members, for the members of the Actuarial Association of Europe, the mutual recognition. Because inside the European Union, members of the European Union, and you can support yourself. Then you are free to move inside the European Union, take a job where you like, take residence where you like, and it's like one country. Inside the Eurozone, you even have the same country. Inside the Schengen zone, your passport isn't checked when you cross the border. So European Union is going to give you the feeling of being in one country. You don't have to be. If I were younger, I wouldn't have to do military service in France. Such a my passport. But I hardly notice. Austria for more than 30 years. I don't notice. So you don't have to do military service, but you also don't have voting. Okay, so that mutual recognition agreement is important, so you can move as a professional between countries. And let me go into more details of that one. Mutual recognition agreement, the basic idea I've already explained. It's a professional work as an actuary in another member country. I mean, if you come from Turkey, you need was working permit. Because Turkey is not in the European Union. But when you are fully qualified actuary in Turkey, you can become an associated actuary in Austria. You have to keep up your membership in Turkey, but then you can work as a professional actuary in Austria. There are no examinations in this. The qualification is expected. Some associations require some practical experience. If you come from Germany and want to work in Austria, you know the language, and the legal framework is about the same. You can read the Austrian law because it's in German, so it's much easier. If you come from Turkey, you might have to use more knowledge of local legislation and maybe some knowledge of the language. Because society functions in German. So if you are in German, but you can be an associated. So a consequence is, of course, that actuarial associations have to keep up with the educational standard, the joint standard. So there are periodic reports and there are also audits. So people visiting Austria, talking to us, find out that our report was fine, that all standards have, it's how it all works in Austria. So it's checked. And also only when you are fully qualified actuary that agreement applies. So we want to exclude exam tourism. So that you say, well, we'd like to be an actuary in Germany, it's a little bit harder. So maybe I take one exam in Italy, I take one in Poland, and then give the because of languages, you take the exams. But that exam tourism doesn't. You can come to us in Austria and say, well, I passed the exam in Italy, that one I passed in Germany. So please check whether you can bring. Check. That's a big plus in Austria. Have your education somewhere. So currently, I'm looking to the former student here from Stellenbosch applied. Of course, she has to do the master because we need bachelor and master. But we check which courses you can recognize for Stellenbosch. Okay.
Some students was financial risk management, right? Was it the financial risk management? The student that you have in your program. Yes.
What yet she will start in
Or she will start with now.
now something.
Oh. So she has to do a master's in financial.
Financial she needs a master in mathematics. Or something related. Or it's easy to do a specific master, otherwise you have to study. You could come to that in a moment. Okay, so that mutual recognition agreement is a big plus. And I was sorry for one candidate coming from the US. It's not extended to the US. So far. Okay, so our local actuarial association, in German, Austria, Austrian Association, German one. Association of Austria, we call it. In Austrian, it's A for Actuar, V for Vereinigung, Association, and Ö for Austria. In German, it's Österreich. Always good. Okay. Also, it's not as old as the German or the Swiss one, but more than 50 years already. Here I have some numbers from the General Secretary. She gave me her slides and she had numbers slightly outdated, but you don't memorize them. Anyway, so we have ordinary members, and from the ordinary members, we have a subgroup of qualified actuaries. So most of them are qualified actuaries. We see an example which is not just an ordinary member, because we require practical experience. as a university professor, because nowadays have to publish. So you don't have time to go for 3 or 4 years to industry and actually work as an actor. So I can never fulfill that requirement of practical experience. But I'm not ready to give up my university professorship. But there's a special clause that I'm teaching financial actuarial and mathematics, and I have the right to do that. After a PhD, you need an additional qualification to be allowed to teach. And when you have that, and you actually do it, you can be master. So that's how it happened to be master, without actually being it. Sorry, I don't really have time to use. So I'm still trying to find out what actually
Aren't we all?
Okay, so we have actuaries on leave or retired ones. So that's important since we require continuing professional development. We have to attend seminars and talks and prove that you actually do that. And when we are on leave or retired, you do. So there are associated actuaries due to the mutual recognition agreement. We have 29 at the moment. And these mostly come from Switzerland or Germany. And some of our actuaries have an additional qualification, called SERA qualification, Certified Enterprise Risk Actuary. I think, yeah, we have 9 so far. We hope for more. We have extraordinary members. Maybe students of our program can join as extraordinary member without being ordinary member. We have supporting members when we sponsor institutions like pension funds, insurance companies, and so on. They can fund and sponsor the society. So our society has institutional memberships, of course, in the Actuarial Association of Europe, it's International Actuarial Association. We are a founding member of the European Actuarial Academy. So that's run by the German, the Swiss, the Austrian, and the Dutch. It's an academy we run together. It's mainly not by German. So I think we own just 10% of that. It's international. Yeah, we are a co-publisher of the European Actuarial Journal. So if you open it somewhere, you find also my name. And we are about signatories and the global SERA association for this. Okay, so coming actually in Austria. So our understanding is that the profession of an actuary is an academic, like a lawyer, like a medical doctor, it's an academic profession. And so we require academic studies, which used to be the diploma studies. Since now we all had to go on with the Bologna process, we had to convert it into bachelor and master. So instead of a diploma, we now require a bachelor and a master's degree. I myself have only have a diploma. And so I passed 4 examinations for the pre-diploma and 4 examinations for the diploma. So 8 exams and the thesis. I finished my 5 theses. That's it. Nowadays, bachelor and master is all exams and so on. Big change. Okay, it doesn't really need to be in mathematics. So if theoretical physics, okay, if you study mathematics to become a teacher, it's a boundary case, but you can work with it. If you have a bachelor in mathematics and a master in statistics or data science, quantitative finance, okay. But there are 20 exams you have to take unless they are contained in your studies. And that starts with stochastic foundations. So we really ask for measure theory. What do we believe in theorem? the Wien theorem, existence of effect measure, and so on. For with integration theory, the limit theorems, eliminated convergence, monotone convergence theorem, so on. Probability theory, of course, the meta-theoretic flotation, mathematical statistics, stochastic processes, you know, the Markov processes, single process, compound process, maybe even continuous semi-multivariate, and so on. And so on. There, then mathematics applied to actual topics. They assume you know them, life, farm life, health, pension, risk management, mathematical finance, actuarial modeling, creating advanced statistical methods in insurance. So it doesn't help to have sophisticated PhD in statistics. You really have to show that you can apply it in insurance.
Do they also cover Novikov condition?
Of course, I teach it in stochastic analysis, but it's not required.
Because that's important.
Of course, in mathematical finance, you don't have to discuss that. I am teaching it to those who want to do an emphasis, and they have to know this proof. Okay. So, and then of course, there are exams to be taken in economics and legal frameworks, so we have to insurance supervision law, insurance contract law, social security law. Of course, that's also specific here. Supervision law, the European rules. You have to show that we have 6 dedicated exercise classes in the foundations, life, and finance. And you have to show 3 or 4 years of practical actuarial experience. If you only did financial management, you really have to show the detail. Work on intensities, working. If you just did trading. So, okay, and that depends about your thesis. If you have a thesis which fits into actuarial application, it's just 3, otherwise it's the wild thesis. I think about large deviations from Markov chains. Similar one, I'm not sure that works. Okay.
Can I ask, are those exams under the auspices of the AAE? Or is
No.
it separate in Austria?
No, they are next. So we have a university-based actuarial applications. So the society says, well, universities offering these courses, just take the exams. Prove that you pass these exams. Okay. In principle, the rules say the association can examine the students themselves. But more than 20 years in Austria, I never experienced it. In principle, they can. So in principle, they can produce actuaries without the help of the university. But in practice. And Austria is a smaller European country, so it has about 1.5 million inhabitants, the size of Switzerland. Germany is about 9 times as much. But it has a larger insurance company, larger than you would expect about inhabitants. That's for historical reason. What you see nowadays on the map of Austria is just it's one remaining part of what it was. It is, and some Austrians still think of being biggest than what they are. But nowadays it's really been moving that doesn't. So that means for that larger area, the insurance sector is concentrated in the capital of Austria, in Vienna. So then we lots of actuaries, lots of reasons. But the country is too small to really have an educational system run by the society. Funding questions. So it's for the society, it's good that the state is paying for the education of the students. So we have a university-based education system, and currently the technical university where I am is the only institution offering all the courses, the complete education for actuaries, besides practical experience. I would like to have the practical experience more structured than it is currently, but maybe my successor substance that you have a kind of fellowship in the industry, that we work in the health insurance part, the life insurance, the non-life insurance part, and so on. As like a medical doctor, specialized, but you have to look into other areas of medicine, so not just specific. But maybe it can. So, what we offer, the curriculum we have tries to share as many courses as possible with the 2 other bachelor's and master programs in mathematics. We have 3 different masters and 3 different bachelors. And of course, we can't offer every course for every program. So we try to have a big joint intersection. So the master program in financial actuarial mathematics that offers 2 specializations in order to have enough students to run the program actually. So in actuarial mathematics and in mathematical finance. So actuaries have to do mathematical finance in continuous time. For example, for that there is some stochastic analysis. But stochastic analysis advanced is mandatory. But if you go into that, you are here specialized in this, we find that we have to addition. So. Okay, so we have these presentations, and now the advertisement part, that's why the university pays some of the training. The master's program in NITheCS English or German required to attract more international students, and I just emailed the secretary. So since most of you, I assume, are not citizens, there's a fee you have to pay. There are 2 fees, and they add up to 750 euros per semester. Maybe last one. I'm sorry for that, but Austria wants to protect money. So international students are very welcome, but the taxpayers silent. So since we are here, we now have a new brochure because the program is in English only since last year. So I have some brochures. More
just ask, is it a 1-year master's?
It's a 2-year master.
2-year master's. 3-year bachelor.
This is
And 3-year bachelor's.
yes. 3-year bachelor program and 2-year master. It's supposed to. What actually happens is I was surprised when I started working in Vienna that not many students study full time because they try to get some practical experience, and the industry, once they have them, they try to keep them. Why don't we also stay during the semester and not just during the semester play? Why don't we work 10 hours more? So I have one global student he just made me 3 days ago. He wants to make a new initiative to finish his diploma. Because he's working full time, he has time. Now we notice how it's good to finish. Let's see. I would help you. Finish. But of course, that leads to the fact that they study longer. They can study 1 year longer and for free, but after that, also payments kick in. compared to what they earn in industry. Well, I'm always the students to finish their studies first, maybe do an internship for 2 months or something like that. They are in short supply, they will certainly find a job afterwards, but they should finish their studies. Some listen, others don't. Okay, so what do I have here? Yeah, of course, as once you're an actuary, here recognized as fully qualified, you have to satisfy certain continuing professional development rules. So you have 15 hours per year, attend workshops, courses, and so on. So every second year, we have a workshop practice in financial actuarial mathematics. Of course, we aim with our students to show that to them what actuaries actually do. And but also actuaries can take it as additional education. And mostly we ask our graduates to report of what they actually do. Then, according to a model they have developed in Switzerland, introduced to the former PhD student of mine, the actual modeling club. So a few times per semester there's a presentation, either by an academic or an actuary or consultant, about a topic which is relevant for actuaries. So a small team of our society manages it, decides on topics and speakers. You can come for free. There's even a live stream normally available. Then the society pays our secretary a flat rate for the organization and the confirmations. Because it's a lot of work. The secretary likes to do it. She gets some extra money for it, fine with me. Usually we find a sponsor to have some food and refreshments afterwards to make it a nice event where you actually you meet colleagues. Normally you go to a company every day in and out. You don't know what your former fellow student does at the other. But here you can then meet him, meet her, and talk. That's good. And also our students are encouraged to attend. They don't do as much as they should, but they should also attend and make contact. And as a society, we are running a profit company. That's an abbreviation of the German title of the company, limited liability. That's important and not reliable for that company. They are offering courses for actuaries for profit, but the profit goes to the society. And they are also we have life tables in Austria. So for annuity life tables, they are for free, and one of the authors is freely available on my homepage. But there are also life tables for pension funds. Pension funds, they have to license these tables and pay a fee, which goes to the company, and the profit from the company mainly goes to this. Some money that comes from these life tables also go to the manager of that company, which is a former postdoc of mine, who actually did all the work for coming up with this after he put down the law. For annuities, was an expert in it, and then he did the other one for pension funds in a similar way. He wrote up more than 200 pages of documentation, which is quite some work. And, documentation you can download for free, but then you want to have the numbers to work on. Unless you're an academic, to prove you only use the academic practices, you can get a free. Okay. At some point, so now I come to the part where we try to attract students. Say about that. So we start early with the children. So there is a children's university organized by a state-run agency. And we usually also offer a workshop where you can invest in the wheel of fortune. So you can invest money in that wheel of fortune and then see whether you are lucky and your balance goes up or down. And you can do a lot of that. You can even calculate the equivalent martingale measure in that case and optimize logarithmic utility. And that's a talk by itself, really. Okay, we try to give a basic version to these children, and they have fun playing it. And the ones breaking the bank, the fastest, they get prizes and so on. Okay, then we have a more serious thing for adults, Team format. The Wien Forum for Mathematics started some years ago. It's a project by our Faculty of Mathematics and Geoinformation, and continues something a colleague started quite early. But when he became a member of the Austrian Parliament, he stopped doing it for time reasons, and a committee of. So every semester we have about 6 popular science evening lectures in German. Okay. Then we have about a semester 150 workshops for Schmock classes. So, and with these numbers are also not the newest ones, but we reached thousands of school children and school teachers with these workshops. So they are actually coming to us and they get a presentation. And so there are also free courses prepared for the mathematics. You know about it, International Mathematics. There's no physics and participated in one for physics. Never about mathematics. And here topics, maybe it's not as catchy in English as it is in German, but so many infinities with political functions, understanding which is what time is it for the sun's transition to the clock time. Statistics, this is all lie. Pattern recognition can be seen into the future. Yeah, mathematics collection from art. So we try to make it interesting with school kids. And so far we seem to be successful attracting them. Whether they study mathematics afterwards, I'm not so sure, but at least they have seen once the university for the site, and they have seen with mathematics you can do other things, not just become a school teacher. I think that's important. Yeah, there's also women in technology, so dedicated events for attracting women to a technical university. Normally, for the actuarial profession, we don't have a problem. It's about even. But when it comes to physics, chemistry, electrical engineering, not some level. So, for getting them to study actuarial mathematics, we have some apps there online. Here's a link. I just showed you the investing the wheel of fortune, you can calculate your life expectancy and so on. They need some upkeeping because software, system software changes. I'm not sure they all still work. This one at least works. And society And also insurance company came just recently up with a new website called Austria Actuarial. And so all my graduates also say something about being an actuary and how nice it is and so on. And posters we use when it comes to exhibitions. And nowadays, watching movies, so they don't read, they watch movies. And we have movies about being an actuary. And mostly in German. So here's a nice former student of us. So he's standing at one of these towers of humans, which is all glass. So you see him standing in front of the skyline of Vienna, talking about being an actor and so on. You just have to finish studies. You just have to manage to finish the studies. That's it. Yeah, I think that's very good. Okay, so we put movies online, since quite some time, as you see. And here they are all linked. Page. We have an info brochure, and most importantly, maybe for you, there's the job market. So that link gets to our homepage, /jobs, and since summer 2000, my secretary or someone helping, but they are posting job advertisements for free for the financial industry, free advertising. But it should be a job where our bachelor or master is a substantial asset. So if they don't want the education offer, they can't achieve. We have to value the education we give to our students. So you can sign up for the email list if you like. It's supposed to inform our students that they are not just born jobs, many different jobs which come with a lot of different titles. But what they have learned or will learn when they study our bachelor master program is useful for these jobs. Okay, and I think that's about the end. It's a lecture series, but otherwise, okay. I think I stopped. Thank you for your.
Anyone else want to question maybe? Okay. Cool. Well, thank you very much. I really appreciate it. I'm just going to talk about appreciation. My wife said this is a nice bag, so I believe that this is a nice bag.
I don't ask my wife.
And you mentioned that you're kind of with physics, and I think you like our coffee is branded as rocket fuel. So, so thank you very much. I really appreciate that. Thank you. And thank you for your time. I appreciate that. Good.
So I have more coffee for the culture. That's just it. Once you play for you, I don't want to tell you the moment.
It's Good, thank you.